the link with the technology, how the technology can achieve, can make it real, this radio and especially 6G. So, Didier,
thank you.
The floor is yours.
Thank you. So I will try to define you which would be the 6G RF roadmap and how can the process, the technology process, will help to go or not to go to this roadmap. So one key feature of the 6G is data rates. And you can see on this first slide, we target 1 terabit per second. So first of all, connectivity or wireless connectivity is everywhere in the world, especially when we need mobility, when we need also flexibility. So we can have wireless in the infrastructure, in the consumer market, in the industry market, and in automotive. Each of them have different key features. For instance, for the infrastructure, the market is in the tens of millions of linear growth per year. And data rate is 500 gigabit per second for 6G to begin. We need dynamic beam and linearity. It is the most stringent applications. Then the consumer, so hundreds of millions to billion of devices. The data rate 10 gigabit per second, and here we focus on the cost and the power. For the industry, millions of devices, and we focus on the interference, the cost, and the power. And in the automotive, it is also millions of devices, and we have the interference, but the latency is very important, and the cost. So what will be the 6G network? Today, the network is mainly a 2D network. In 6G, we will have a complete 3D network. This means that you can see we have SATCOM. We have also UAV relay. And we have the classic big cell network. And between each big cells, we will have the small cells to have a densification of the network and to increase the data rate per user locally. Obviously, we have intelligent IoT in the smart factory. We can use light at home to transfer data. We have the mobility with the car, with the bus, with the boat, and everything will be connected. And the target for the 6G is that everywhere you will be, you will have the same service. And if we look at the spectrum allocation, so today we have the 5G spectrum allocation from 0 to 70 gigahertz, roughly. The beyond 5G is the next step, 24, 27, with the bands between 70, 75 giga to 110. And then for the 6G, we will open new bands, so the D band, between 110 to 200 gigahertz, roughly. And after that, in the next part of the 6G, we should open bands, G band, H band, J band, between 220 to 300. It is forecasted that after 2035, we should open bands in the 400 gigahertz range. So you have the list of the different revision here, 3GPP release, the WRC 2019, and the next one, which is the 6G new frequency generation. And 6G will exist if we don't impact, or we don't have a high impact on the climate, Earth climate, and especially if we are compliant with the Paris agreements. So what does it mean? Today, you can see the green line, which is the expected evaluation of the CO2 emission of the telecommunications. So today we're somewhere between 4%. This is the global CO2 emission of the aerian traffic. And if we don't do anything more, especially in the efficiency, in the power efficiency, we should be in 2025 at the same level of the terrestrial transport. So this means that our field, the telecommunication today, is not in the radar. I don't know why, but we are not in the radar. But if we become in the radar in the next time, you will see that this will be an issue. Because if you look at the road transportation, today road transportation is in the radar, and we speak about electrical cars, we speak about everything. The flight transports are in the radar, but they don't emit more than us. So with this, the organization like 5G AI, which is a European organization for the 6G ecosystems, forecast to increase the power efficiency in the telecommunication network by a factor of 300 between 5G today and the 6G network, which is huge. And if we look at what the IRDS is the International Roadmap Device and System forecast for the RF. This is between today, so 22, yes, and the 6G 2035 for the transceiver to increase the power efficiency by 14. What does it mean? If you look at what they say about the 5G 2022, they say that the maximum data rate for a transceiver is 5 gigabit per second, which is roughly high for the moment. And the power consumption is 200, 300 milliwatts. If you look at what will be the case in 2035 for the 6G, the data rate should be 70 gigabit per second for the transceiver, and the power consumption is exactly the same. So this is a roadmap So this is a guide for us. So for the wireless and RF, we face two walls. The first one is how to transfer analog data rate into digital data rate, or the opposite, with ADCs. And the second one is the power amplifier limitations. So for the ADCs, the limitation is mainly the power efficiency when we increase the sampling frequency. And if you have wideband to transfer, you have to increase the sampling frequency. And you see the 5G area, not the 6G. 6G is on the right of this one. So the 5G area is somewhere where the ADCs, for this example, are not efficient. If you look at the power amplifier output power, you can see that under 100 gigahertz, you have solutions. Over 100 gigahertz, for the carrier frequency, the solutions are very low. So we will come back after on these 2 points. So what does it mean? The process technologies will not answer to all the questions we have. If we look at this classic transceiver, we have different area. We have the conversion area, ADC DAC ADC, sorry. The frequency synthesis area, the power amplifier area, and the low noise amplifier area. For each of them, we have issue to solve. For the first one is the sampling frequency. For the second one is the frequency and of the PLL. So we need to distribute local oscillators, which are at very high frequencies. So we should have high phase noise. We should have difficulty to create the frequencies. For the power amplifier, the issue is that the carrier frequency is at a very high frequency with wideband, and the classic processes we use for the civil market can't aim these frequencies. And for the low noise amplifier, obviously, this is the noise figure at these frequencies, which are very high. So we have to rethink the architecture. We have also to rethink the process integration. Our main target for civil market is always the cost. Power efficiency, cost. So the first challenge, which is the wideband. So we mainly see this wideband on this graph, which is, for instance, for this is the ADC, but we have the same for the DAC. And you can see the evolution of the form, so the form which include the power efficiency. You can see that for low frequency, low sampling frequency, we can increase the form. But for high frequency, high sampling frequency between 10 giga and more, it is not so obvious. So you can see that if you, at the limit of the low limit of the 5G at 10 gigahertz, you lose about 20 to 30 dB of efficiency. So the first question is how to work with these constraints And you can see the evolution at high frequency is not so important. And whatever you design in ADCs and DAC, whatever are the technologies, you have this limit. So you can do sampling at 10 giga, 50 giga, and so on. It exists, but the power consumption is too high. For instance, to have something between around 5 gigabit per second is you have an ADC which is consuming approximately 1 watt, which is not compatible with your iPhone. So we have to rethink the architecture. The second one, if we think, yes, but we can use CMOS in nanometer scaling, so less than 10 nanometer, 5, and so on. What does happen with that? If you look at the curves, which are the FT is increasing up to something around 15 nanometer node, and then it is decreasing. The GM is always decreasing at between 15 and less, and the VT is also decreasing. So this means that the CBOS technologies will not answer to this challenge. So we have to rethink the architectures. So what about multi-band, multi-channels, digital IF? We have to rethink it. It is not working like that. What about also AI management? So a few examples of trends today. You can see this one from Intel. So they are using 15 gigahertz bandwidth, which is not very low consuming, but they are looking to do a multi-bands approach. QUL, they are working in a complete digital transceiver. So they put all the constraints on the power DAC or the LNA, digital LNA. So they say that it is a good solution, but the issue is mainly on the last RF stage of the transceiver. So the next one, you can see this is a Leti trial. So they use 60 times. So they program to use a number of times 2.16 gigahertz band, so the channel. So this is a multi-channel aggregation. So the issue in this one is mainly on the frequency synthesis. You need to have a multi-LO with a space of 2 gigahertz. Whatever, this is another solution. And finally, I would like to speak about Hermes. So in Hermes, so this is work done by François and other groups, Letty also and other groups. The idea is to push the pressure, if we can say like that, to an analog signal processing. And the idea is to use a specific mathematical basis where we project the signal and we just convert the coefficients. So we have not, the conversions is very simple. the frequencies are very low. For instance, we are here with 64 coefficients. So we have very small constraints on an amount of converters, but the constraints are very low. We will see after. And in addition, we can put artificial intelligence which plays with these coefficients. So now going to the RF power challenges. So coming back to this graph, you can see the different materials. So the silicon LDMOS, the silicon CMOS, the silicon germanium HBT, the gas ANT or HBT, the GaN ANT, and the INP HBT or ANT. What you can see with this is that under 100 gigahertz, the carrier frequency of carrier frequency, the GaN PAs are the best in class. Over 100 gigahertz carrier frequency, the INP are the best in class, but they have to be benchmarked to a CPA because they are not cost effective. They are used for military activity mainly. So if we look at the wafer, the best in class cost effective is the 12-inch silicon wafer. So is it possible to do a GaN over silicon and create GaN over silicon 12-inch wafers, or INP over silicon in a 12-inch wafer? This is questions we have today, and we try to answer to these questions because the limit of the silicon, the pure silicon transistors, or silicon germanium transistors, show that we can't address the last part, which is the 200, 300 gigahertz. And in addition, we can't have high power under 100 gigahertz with silicon. So this means that we have to find a path to go to high efficient PA with these materials, GaN and INP, but high efficient, cost effective PA also. And always we will do benchmark with SiGe and SOI. This is another representation of what I told you. Under 100 gigahertz, you can see that you have plenty process which can answer. The CMOS is well placed. In the 100 gigahertz to 300 gigahertz, SiGe and GaN are well placed. Over 300 gigahertz, the only technology which gives us margin is INP. So this concerns the PA, so the active, if we can say active part of the transceiver. In the transceiver, you have also the antennas, especially when we are in millimeter wave or sub-terahertz communication. The antenna is the part of the equation. And you can see here two kinds of antennas. The first one is the low gain antenna. So low gain antenna is an antenna which radiates everywhere. And the second one is the directional antenna. so you radiate in a small part of the space. You can see here the level of the power we need for the user and for the base station. So 40 dBm radiated power for users and 60 dBm radiated power for the base station. You have on the x-axis the number of antenna arrays, so 3.5 by 3.511 and 35 by 35. You see in that case that the transmit power, which is the power transmitted by the PA, is reducing when you increase your antenna array. So this is an example at 140 gigahertz. This means that with 0 dBm transmit power, I need somewhere an antenna array of 300 antennas. So is it magic? Yes and no. Because if you focus your power in one part of the space, that means that you transmit efficiently. But if the mobile is moving, you have to follow the mobile, because if you don't follow it, you lose your communication. So that means that this is interesting, but bigger is the antenna array, higher is the difficulty to follow the mobile. So you need beam forming to focus and to orient your beam. So this is an increase of complexity in your transmitter. But this is a part of the solution. A few examples now. One thing we have to do is in millimeter wave, you can't lose power between your circuit, so your power amplifier, and your antennas. And in the same way, you can't have loss between your antenna and your LNA. So this means that the solution is somewhere in antenna in package or antenna in silicon. Antenna in silicon is not very efficient. So people are working on antenna in package. This is an example of one group which is in Europe, one of the leader, which is the Fraunhofer ICDM. Another approach, for instance, this one from Leti. Here, they have done an antenna array at 300 gigahertz. So you can see that the antenna array is about 20 millimeter by 20 millimeter size at 300 gigahertz. Each antenna, if you look at the smaller graph, is something around 250 micron by 250 micron. And with this kind of antenna, they have a peak gain for the antenna of 32 dB with an aperture efficiency of 36.5%, which is very high. Obviously, you can't use this kind of antenna without beam correction. So you need to have, in addition, phase shifters or procedure to modify the orientation of the beam. For their application, they use pin diode, and their correction is simply a step-by-step correction. So that means that you active or not pin diodes, and you modify your steps. But these pin diodes are in INP, which is not a low-cost solution for the moment. So we will look now at use case examples. So as I told you, depending on which use case you will target, you will not need the same data rate, the same distance, and so on. So the first one is more an indoor connection. So device to device, kiosk, automotive, so in-cabin automotive. So it is short range, it is a point-to-point. Distance are low, less than 5 meters. Typically, few centimeters to 1 meter is the main part of the market. The data rate somewhere between 10 gigabit per second and 50 gigabit per second. This is a very interesting use case for silicon. And either if you have a very low distance, so a few centimeters, you can imagine to have a pure CMOS solution for this. The second one is all the mobile hotspot, mobile user, mixed reality, and so on and so on. So this is a point to mobile. So this means that if you focus, you have to follow. You have, it is a mobile indoor, but it can be also outdoor. The data rate is limited to 10 gigabit per second. This is what is targeted with the 6G. 6G targets 10 gigabit per second per user everywhere. Distance, 10 to 100 meters. So for this, you need specific technologies. So INP or GaN to address the 100 meters. Then the fixed wireless access. So fixed wireless access we can say that it is a kind of a micro cell. So you have the mini cell and the micro cell. The micro cell are somewhere, for instance, here you can have a micro cell. This is the next generation of the Wi-Fi. So this means that the only difference between Wi-Fi, so Wi-Fi today is not a cellular application. It is an indoor application, and you have then to go to the cables and to go outside. The fixed wireless access will be a cellular approach, but it will connect also your laptop, everything. The data rate in that case should be 20 gigabit per second and the distance 100 meters. And you will have this fixed wireless access everywhere indoor. So for instance, in theaters, in stadiums, in mall, and so on. For this one, we need also INP, and we need also GaN. The last one is the most stringent. So wireless backhaul fronthaul, 500 gigabit per second, more than 100 meters. So the difference between backhaul and fronthaul. The fronthaul is the link between the antennas and the base station. The backhaul is the link between a base station and another base station. So for this one, it is clear we need GAN, we need INP, and we need a lot of innovation in the architecture. I have not on this presentation the SATCOM, but SATCOM, as you have seen at the first slide for the network, is an important point. So SATCOM will be mainly LEO SATCOM, so the low altitude satellite, like Starlink and so on. For this one, the data rate should increase to something close to 10 gigabit per second. And we need also technologies like GAN, INP. So now one point I would like also to address is that in 6G, the radio should be smart and flexible. So if you want to increase your efficiency, you have to transmit only what you need to transmit, and you have also to transmit it where there is no noise, for instance. So if you have a crowded spectrum in the 5 giga, 10 gigahertz band, and if you have no noise in the, for instance, 55 gigahertz band, choose the 55 gigahertz. Maybe it is more efficient. So if we come back to the Hermes project, we have in the Hermes project a wavelet projection and edge AI. So this brings flexibility and ultra-wideband processing. So the mathematic basis is a Walsh basis. So we do Walsh projection, and the AI plays with the coefficients of the Walsh projection. This project is done in the 20 nanometer generation of the FD-SOI. And the architecture which is in place for this part, which is the, what we can say, the baseband conversion or the AIF conversion, will benefit of the scaling down to 10 nanometer. Why? Because we will have FT, we will have also more density in the CMOS transceivers, and we can also, with the FD-SOI, work on the power consumption we need locally, using the backgate to cut or not the power consumption. In the same time, you can see that the mixed analog RF part will be mainly in silicon, but CMOS or BiCMOS. And for the last one, which is the PA, LNA, switch, filters, and so on, 3.5 should be the solution. And what we need in this kind of architectures, we need IFTF max FD-SOI. We need fast AI reactivity. the backgate will bring the flexibility. And obviously, with the 3.5 high frequency part of the transceiver, we did RF 3D integration. So the idea which is followed for the next generation is to rethink completely the transceiver. You can see that in this part, the PA-LNA is not rethinked in terms of architecture, but more in terms of materials. The yellow generation is a big work area. We have to do very high frequency LO generation, very accurate LO generation. So there are solutions I didn't speak about today, but for instance, in Leti, they are working on a TORP LO generation. The TORP LO generation is that you have a reference, for instance, at 2 gigahertz. This is that they use in their circuit. And you create a multiplication of this reference. So not one multiplication, but numerous multiplications with a step of the reference frequency. So it means you have a 2 gigahertz. If you want to do between 110 and 130 gigahertz bands LOs, you have one LO at 110, one at 112, and so on and so on. So this is a possible solution. Then the up-down conversion, for the moment, the architectures are not completely rethinked. And for the signal processing, to reduce the constraints on the converters, we have to rethink completely the architecture. So I've presented here one solution. There are other solutions in this way. All of the solutions are trying to reduce the constraints on the converters. So I think I have finished my presentation. So yes, and we have time for questions.
So time for question here in the room or online. Any question about technology, application? Yes.
And about there's something more about the antennas. Because you mentioned that they are going to be on chip. From more technological point of view, there will be any change.
For the yes, I have just one side on the antennas. They are worked on the antennas. You have different solutions. You have I have seen antennas with a kind of reflector antennas. So it means you have one antenna which go to a mirror, so electromagnetic mirror, and then you project it. So then that means that if I modify slightly the angle of this first antennas, I modify completely the angles of the other one. So this is one. You have also meta materials in the antennas to increase the gain of the antennas. The antennas are passive, but they are becoming to be active. So they use, but I am not a specialist of this, but they use metamaterial to increase the gain. So it means you have a power which arrive on the metamaterial, and the metamaterial reflect higher power. So this is another way to increase the power without increasing the focus of the beam. So this is another way. All of them are under study in different groups. And the main drive for them also is the cost. You can use metamaterial, but if you use metamaterial and the metamaterial is 10 times expensive, more expensive than classic, it will not the solution. But they are looking about these things. Last point, I am not in this point, is this reflective
and there were
IS.
reflecting surfaces,
Yes.
intelligent reflecting surfaces. There were
intelligent
questions about that.
surfacing, yes, the RIS. So the idea is that you have not to transmit to a very long distance, especially in millimeter wave and sub-terahertz. Everything is a wall. So you have a tree, it's a wall. You have everything is a wall. So the idea is to have this RIS surface on the wall in the streets, and you transmit your beam to one part, which goes to another one, and which arrive to the phones, which is here you can't have in line of sight. So this is other solutions. All of them are under study. Today we are in the early phase of the 6G definition, but all of them can be prospect.
Other question in the room? We have one question online. It says that I'm unable to get the importance of AI models in the baseband in RF 3D integration will be done by data-driven models. So
Yes, I am not a specialist of the AI.
maybe I'm going to answer that question in the next
Yeah,
talk.
yeah, maybe,
Yes, with the
maybe,
baseband
yes,
and,
maybe. Yes, so
yes,
just
yes.
to be simple, the idea is that the AI learn about its environment, and we can bring to the AI, for instance, the spectrum, all the spectrum availability, yes, and it decides to transmit in this part. I think that Emilio also 2 days ago spoke about semantic. The semantic is clearly AI activity. The idea is that the AI becomes a kind of manager of the transceiver and decides for the transceiver to transmit at this frequency with this modulation and with this part of the message.
Any other questions?
Just one question. As your simulation, the distance between outcomes is 100 meters.
So can you speak loudly?
We cannot hear you, in fact.
Yeah.
The distance of the transmission is about 100 meters
Yes.
from your example. And I want to know the 100 meters, it's a limit for the simulation or just
No, it's not. It's not a limit. After it depends on what you are doing. For instance, you can transmit with the. You can receive data or transmit data to the LEO satellite, which is at 300 kilometers. So this is not a limit. The limit of 100 meters here in the infrastructure is for the mini cell, because what is thought for the 6G, for the cell, the transmission at very high data rate will be done as today with optical fibers. But a mini cell can be, a mini cell is somewhere on a light in the street, somewhere close to, I don't know, a bus stop or whatever. So the idea is that the mini cells are not are very flexible. So if they are flexible, they need to have wireless communication, and they need to transmit the old data they have to another mini cell, which transmit to another mini cell, and so on. So distance is roughly around 100 meters. So the solution we are trying to find are around 100 meters for this case. How many mini cells?
No, only for mini cell for those distance.
Yes, for this distance is mainly for the mini cell, yes. Mm.
So there is one question online, one remark, but I think I will answer that in the next talk. So training and testing data sets will be created by experiments to feed
Yes.
the AI. And that I too working in automation of AI requires huge data set. So are we looking for S parameters of the system or any other data set? And the answer is yes, we are looking for S parameters, and we are going to feed the AI with S parameters to linearize all that. So it's working in automation of PA, and we'll be happy to connect. It's a question on the discussion. Okay, in the chat. Any other question? Yes?
Actually, it's more about the architecture of the TRS. One of the architecture you said they use multi-actors with a separate parameters of 2 points in gigahertz. So every TRX has multi-actors with different frequencies.
So you speak about the architecture to go to sub-TRS.
Yeah.
So that yes, there are different solutions. If we speak about the multi-channels, the idea is to do at the end an aggregation. So aggregation means that you have to use a power combiner. So there are two schools now for the power combiners. One, it is the power combiner in the die with classic copper power combiners.
Architecture isn't a limitation for the.
So the limitation is in this part. The power combiner is loss. So this is one limitation. The other limitation is how to do the yellow. Another way now for this is to do the power combination in the air. So in that case, the limitation is on the antennas.
Yeah, for the frequency limitation for every TRX.
Yes.
So if you need, let's say, 16, and you have a 2 point something gigahertz for the 16. So
yes.
every user will
Yes. So if we speak about sub-terahertz approach, the communication will be focused. So that means that I have this point and this point which are working together. They use, for instance, 30 gigahertz around 300 gigahertz. If you have this point and that point which are working together, they are using the same frequency.
And the same frequency can be used by multi-users or different.
So for multi-users, it is different. It is at lower frequency because you have one point, for instance, mini cell, which address different users. So for this one, it will use, for instance, the first bandwidth. For this second one, which is close to this one, it will use the second bandwidth. But for this one, which is far from this one, it will use the first bandwidth. So the advantage of the focusing and and following the mobile is that you can reuse the frequencies.
Okay. So I think we can thank again Didier for his answers. Thank you for the question. So, and just to answer online, I will talk about it in a few minutes.
Okay.
There's again some question about AI.
Okay. Yes.
How to analyze it. So now I change the presentation, and this one I can think you. Can you see it? Is it okay online, Pierre? Okay. So I will talk. I will talk in the continuity of what Didier introduced about the technology. But as I don't know your background, we'll talk about communication, their history, and how it could be used to artificial intelligence, and make the connection with the first keynote talk you had on Monday afternoon. I don't know if you remember about semantic. So I will take the time. We're in summer school. I have more than 100 slides, but don't be afraid. I go quite quickly over it. And the slides are very illustrated. So see, we start from the communication, we go through the technology, and we end at the future of communication. And I will explain again the same principle about frequency and what is power consumption and the link with the technology, etc. Maybe you have already some background about it, but well, let's say it's always good to refresh our knowledge. So about communication, well, it's easy to say that everyone is communicating. I'm communicating right now thanks to the sound and also to the animals. Yes, you have wolves speaking bats. They use ultrasound, you know. It's like a radar at the same time like the dolphin as well. So it's about wave. It's always about waves to communicate. And same, we have bees. So I don't know if you knew, but here in Bordeaux, the symbol of our engineering school is the bee. Yes, yes. Every engineering school in France has an animal. So for us, it's the bee. And the bee, yes, use dance to communicate, and also they use their, you know, their, how do you call that? Well, their feet to, yes, to make some noise as well, and to produce other kind of communication. And us humans, of course, we communicate since ever, and our first way to communicate was optical communication, especially with smoke. Well, that was coming from the old ages. Do you know Lucky Luke? No, this character? Or is it purely French? I don't know. No, yes, in the Netherlands, you know it. Yes, yes. I don't know in Europe. Well, it's very common. Well, the Indians from America were used. The natives, the natives were used to communicate with smoke and also with sound. But it's still the 19th century. We use that optical way of communicating. And you have a very famous French who invented what we call the kind of optical telegraph. His name is Claude Chappe. It's in southeast of France, and you can still visit some. So every 10 kilometers, you have those signs, and they were encoding the message using those optical signs. So end of 18th century. And then after came the telegraph to communicate. The fact is with the telegraph, you need to encode everything. Yes, beep, 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 beep. So this is where we start to convert the message we want to send, the way we're communicating, under something discrete. It's not 0 and 1, well, it's kind of, it's dot and I don't know what the English word for that. You can see my English is limited, so I don't know how to communicate that, but the tiret. And it's because of technology, then we shift more and more under something non-optical, which is more electrical, and this is why we are here today, especially with Mr. Faraday, who discovered that charges can interact together. When you have a plus, a minus, and you know all that, well, I'm always connected to food. Food here is an urchin. Have you tried that, the urchin? Yes? Especially well, in China, I've had some. It was in a Guyane, very nice. They know how to cook it. You have to try that once in your life. And this is exactly the same. You have those lines of electromagnetics, lines, fields, etc. propagates. And we can play on it with positive and negatives to modify those fields and to use it as a way of communication. And this is what has been demonstrated by Maxwell. I always say to my students that Maxwell is the beginning, the foundations of everything when we want to communicate in EB, electromagnetic fields. The 4 equations of Maxwell are the base of everything. What does it say? It says that every electromagnetic waves propagates under a sinus or a sum of sinus harmonics. There is nothing brutal in the nature. It's just sum of sinus. So sinus, continuous wave, are the base of everything. And this is exactly what Maxwell said. Have you learned about that, Maxwell? Yes, with the gradient and all these difficult equations, and now I've forgotten, maybe some of you are still using it. But there were a meaning when you were studying that in physics, and that can be summed just about continuous wave. So this is where he used it, and it was applied, and Hertz, so you know that word Hertz, but it's very old man, Hertz, there from the 19th century, has observed that something oscillating will propagate through the space under an electromagnetic wave. We are still using the Maxwell equations and then propagation, electric field. This is well observed, so you can imagine that in the lab, there were not many tools for that. It was more like you see what happens when you connect things, and oh yes, oh it moves somewhere at the other, and you ask yourself a question. Yeah, it was more about observation and then how to use it. It's engineering, and there's a huge debate in the world. Who has invented first radio? So Italians, we say Marconi, of course. Yes, Russians, no Russians in the room. Yes, they will say Popov. Okay, and for us, French, we say it's Brownie. All this combined together has created the radio because everyone has provided a part of it. As I said, Hertz have proposed the way to generate an electromagnetic wave. But then Popov also assembled the antennas. Brownie worked on the receiver, how to then collect the wave and how to tune to the frequency. And well, Marconi has made the first demonstration. That's why he's recognized as the inventor of radio, let's say, worldwide. But I have this discussion many times, especially in Brazil. I know there's a Brazilian guy as well who has invented the radio. Is not there, but every time I go to Brazil, they say, no, it's Brazil who invented the radio. Come on. I don't answer. I say it's more a common invention. See, so it's beginning of the 20th century, and well, Marconi at the end gets the Nobel Prize. Well, that's life. So before Marconi, several engineers also experienced that. It doesn't come from one man, it comes from others, and others tried. I didn't know Mucci, so I think he must be Italian. But the other one, you know him, Graham Bell. Do you know Graham Bell, who invented the phone? I think he was deaf, but he invented this to communicate. We still find from Hertz some invention that provided also the basis for the radar. So all this application accelerated the transceiver radio communication development, and this is what we are using so far now in our smartphone. It's all this invention, except that the principles are still there, the technology is not the same at all. And we make the connection with technology. Well, it's purely on the news right now. Maybe if you have heard on the news since 2 days, there is a submarine which is lost. I hope they will be saved very soon. But the Titanic was the very first application for telecommunication. This is where we have learned that communicating in real time, being connected is really important. When they sent the very first warning message, SOS, using Morse, we understood that communication was really important. And there's another important fact about Bordeaux and why you have here a microelectronic lab here in Bordeaux. Do you know that? We don't have any industry here in Bordeaux about that. It's more about wine, food, maybe the forest. Why do we have electronics? It's because the same, in 1914, when the Germans decided to enter France, yes, beginning of First World War, I don't know if they decided or we decided, but well, they came very close to Paris in the first coming months, and the French has to answer very quickly how they did it. They used the Eiffel Tower with some wires there on the Eiffel Tower and asked to all the taxi to bring some soldier and then to counteract the Germans. Then we understood that radio was really important to synchronize and, well, for the army to act. So we need some engineers for radio development. And so, okay, we need to train engineers. What would be better than an engineering school to train engineers? Yes, okay, let's open an engineering school in 1920, just after the First World War. Where are we going to put that engineering school? In Paris? No, too big. Well, close to the German border, maybe they can come back again, yes. As far as possible to the German border. And where is it? Southwest of France. What is the main city in southwest of France? As far as possible, Bordeaux. That's why you have here that tradition of electronics, of communication here in Bordeaux. Everything can be explained. As I said yesterday, every time I have information, I like the little story behind it. So, well, we see that communication during wars are really important. I didn't know that during the Second World War, this is when came the talkie-walkie, the very first wireless communication there. So I'm not going to detail all of it. What you have to remember is that mid-20th century is you have some very heavy equipment for communication, and the autonomy is very limited. So several kilos for few minutes of communication and just voice. So how do we evaluate from this middle of the 19th century when it was purely wired to our wireless today's? And I think you know that picture, everyone has a mobile phone. The very first mobile phone, let's say it's mid-20th century. And I think that Tesla, beginning of 20th century, just envision that everyone will have a wireless apparatus in his pocket to be connected. Well, this guy was amazing. He wrote that. So Bell, it's same as Graham Bell, but the Bell Labs are the innovators in terms of technology. Every time you have a new invention, it comes of technology, it comes from the Bell Lab. And they produce the first technology. So I was talking about the transistor, it comes from Bell Lab, and so on, all the development. But this is Martin Cooper, who has invented the first smartphone in the 70s, and also it was quite common because of science fiction, and I will talk about it after. I mean that everyone was envisioning at the other half of the 20th century that we can communicate wirelessly. So I don't know if you know Captain Kirk. Yes, no, I know that Mike and Jordi said that they don't know about Star Trek. Yes, no one knows about it. It was more about my generation, I think. You know about Star Trek. So Martin Cooper is the very first inventor, and this is the first, not smartphone, first phone, wireless phone. So like the talkie-walkie, 9 hours to recharge the phone for, I said 6 minutes of communication, but I would say 20 minutes, and that's it. And then the whole night you need to recharge. How often do you charge your phone? Every day, yes. Who knew the Nokia 3310 phone? Yes, the one with just a screen, where you can play with the nibble, but just to play. No, you didn't know it, and it's too old for you already. This phone, you can keep it during 1 week without charging it. Yes, but it was just to play some communication, and more than 20 minutes. So, what makes the difference for that? it's the technology and its evolution. So Didier gave a lot of details. I'll go very quickly on it. What we've changed, we went from discrete electronics to integrated one. And I will repeat that once again. And that was a game changer. Integrated circuits changed everything in the 70s. So it started with the Bell Labs again, where the first transistor was invented. So by Shockley, Bardeen, and Barton, it gets several years to be patented. And then they have the Nobel Prize for it because it changed everyone's life. And you have this is the very first transistor. If you go to Washington, the city, District of Columbia in the USA, you go to the Smithsonian Museum. You see the Capitol, the Capitol with the Congress, the American Congress. On the right, there is a huge museum. You go to the first floor, left, last room, on the left again, and left corner of the room, there is the very first transistor there. You can see it if you want, if you visit Washington. I've been there and I saw it. And at the same time, you can see the Apollo 11 capsule also. There are many things in those museums. So they've created the very first transistor, but the fact is that Shockley was not such a friendly guy. He was the brain, but not so friendly. So please be human and be kind each other. That means that the people working with him decided to quit his team and to build their own company. And their first company was called Fairchild, with Noyce and Moore. And I think you know Gordon Moore. He passed away 2 years ago, I think, or 1 year ago, something like that. Is still alive?
This year.
This year, okay, see? Just passed away, but he invented the Moore's law. And same after Fairchild, he decided to create another company, which is called Integrated Electronics. And if you merge integrated electronics, that means Intel. He has created Intel. So everything we are using is coming from there. And then Jack Kilby invented the very first integrated circuits. The very nice thing about Jack Kilby, he was very young when he done that. He came for like a kind of internship or introduction in the company. He was new, working with other engineers, but as he was new, he was not allowed to go on vacation. So he had to stay and work in July and August. And the other engineers were on vacation. When they came back, well, Jack Kilby had the time to assemble all the ideas to design the very first integrated circuits. And at the same time to patent it. So the patent is from Jack Kilby. The Nobel Prize is for Jack Kilby because he stayed and worked during vacation. So I'm not going to promote that you have to stay and work during vacation, but this is exactly what you are doing right now at the summer school. So this is how came the first integrated circuits. It was a few transistors put together with resistors to have everything on a single die. Okay, and then we pushed more and more the technology to make it smaller and smaller, to integrate more transistors, more processing capabilities, and then at the end, to have the first microprocessor. That was a game changer, again, in our lives. We can process digital information. And there is a Moore's law. The Moore's law is still up to date. That's amazing. When I was a student like you, we said that, okay, it's going to be the end in 2005 or something. Last node is 100 nanometer. We cannot go beyond that. Well, I did my PhD with 65 nanometer technology. Okay, we went beyond and said, okay, after 20, it's over. Now we reach the latest node, is 2 nanometers, something like that. We're still pushing, and pushing. Well, I was speaking about digital, but let's apply that to analog. And analog is about radio frequency. The fact is with radio frequency is that we share the same resource. And those resources are the spectrum. If we speak at the same frequency together, we are not able to understand each other. So everywhere we need to have like a policeman saying, okay, at this frequency, you have to speak this way and to behave with other users this way. So everything is described as a standard and everything is standardized from 0, well, let's say few hertz, I think it's 3 kilohertz, up to 300 gigahertz. And everywhere in the world, you have like a policeman, okay, watching what you do with the spectrum. And everything is a standard using the IEEE. So I told about IEEE with sponsoring that summer school. IEEE is researchers, is industrial getting together and saying, okay, this is the way we are going to communicate in the spectrum. So as you can see here, different parts of the world, different frequencies, but it's quite the same. When you were very young, we were not able to agree with each other. And in your phone, we have several chips because several countries didn't agree to speak on the same frequency. So you have to buy a new phone every time there were a new standard. That was more than 20 years ago. So we're talking about the antenna, saying that just the frequency and the antenna are two things connected. I mean that the higher the frequency is, the smaller the antenna is, but it's gonna also have some implication about the design. I'm not an expert about that, so I'll go quite quickly over it. And what is important, I don't know if you have that background, is when you have an information, it's gonna be in what we call baseband, from 0 to few hertz, kilohertz, megahertz. That's the container of the information. I cannot share it with you at that frequency. I need to place it on the spectrum somewhere to find a room to communicate it. So the way to do it, same, we go back to Maxwell. We multiply that information to what we call a carrier frequency, which will place our channel in the spectrum. I'm used to say to my students that it's trigonometry. And they have learned trigonometry at high school, say, but I don't know why I'm using it. Now you know there is an implication every day about trigonometry. So when you multiply two cosine, A and B, well, what you have at the end is the sum, A plus B or A minus B. It's the carrier frequency. So here it's FP, because P means porteuse in French, which means carrier in English. You've learned another word today. So you can up convert in the spectrum and down convert thanks to cosinus and Maxwell. Easy. It's just about physics and trigonometry. What you've learned at school is very useful. Here is an example of how you can down convert to 5 megahertz or up convert to 5 gigahertz. And this is the architecture, Didier shown, but a simpler one. With the antennae, then you have a filter because you need to remove the unwanted frequency when you have that product. And this is the mixer there at the middle with the hex that will up convert or down convert the signal. So you find all these building blocks, the mixer, the signal that you receive or either you transmit through the antennae, and the carrier is generated by the local oscillator. Here you have as a second signal. That's why at the end, after the mixer, you have either the sum or the subtraction, either you up or down convert. And then you need to filter to remove what you don't want. So there are many architectures for that. It gets more and more complex because there is always a trade-off between the technology. It's not because you have here a nice drawing that it's going to work in the real life. We have to struggle with the specification, the performances of each building block. And this is the whole story of radio frequency since 40 years now, how to adapt it to go higher in frequency. So here you have the example of the heterodyne, the homodyne architectures, and I don't know if you are familiar with it, but you can see there's always some mixers, filters, antennae, power amplifiers, low noise amplifiers. We need always to up, down convert, amplify, and filter. Every radio is built like that to access the spectrum. And same again, I was talking about the antennae, and there were a question about the distance in 6G particularly. The fact is, when you propagate, there will be an attenuation. The attenuation is coming that we are living on Earth, and there is an atmosphere. The atmosphere is made by 80% of, is it called nitrogen? Yes? Yes, nitrogen. The word in French is different. So. Nitrogen, then you have a little bit of, well, more than a little bit. You have roughly 10% of oxygen, and then other gas. These gases are made of molecules. So we come back to Maxwell again. EB fields will interact with the molecules in the atmosphere. So you can imagine that the power will be attenuated through the propagation of the waves because of the molecule in the atmosphere. And it's going to change with the frequency. It's not linear. It's not flat. Some frequencies are really, they will attenuate a lot the electromagnetic wave. For instance, 60 gigahertz. This is the rate of absorption of the oxygen. Oxygen will absorb all the energy at 60 gigahertz. So if you don't want to communicate so far, use 60 gigahertz. You will be limited to a few centimeters. If you want to communicate in long distance, use less than few gigahertz. And that's why at 100 of gigahertz, it doesn't go that far. 100 meter is quite a max. Then otherwise you have to bring a lot of power, and it will be very hot in the room before that you can send a wave. So here is, again, another example of a circuit of a transceiver. See, many blocks, it gets complex and complex. And that's quite a basic one. You cannot imagine the complexity of the radio in your smartphone. So how can we carry an information using those waves? We use modulation. So I don't know if you have the background of modulation. We are going to modulate the wave to carry the information. And there are only three things you can change in the wave. Not the sinus, not the cosinus. This is mathematics. You cannot touch it. But there are three things that you can change under it. So we have the carrier, as I said, and you have your message. Here it's a sine wave, but it can be 0 and 1, as you can imagine. And that carries anything, any kind of message. So three things you can change. A, the amplitude. Yes, you can amplify more or less the amplitude of the signal. Then second, the frequency. You can change the frequency. So the frequency modification, variation, will carry the information. And third, the phase. You can be in advance or delayed. And those three will be able to encode the information in the wave. And that wave, you multiply it to the carrier, and it goes high in the spectrum. This is just radio. This is easy, quite easy, yes. Why do we need an engineering school to learn about that? Yes. There are so many other techniques that makes it tricky because radio frequency is about sensitivity. Every small modification can affect completely the message, and this is what we are working. So here you have two examples. On the left, the frequency modulated signal. So you can see the frequency changing with the value of the message there. And the other one with the phase. The phase of the signal is either more delayed or in advance. And sometimes you can see it goes back completely reverse. So all that together, well, has brought the science to build the principles of the radio. And now we have the technology. So what we do with the two of them? We combine all these principles and we integrate it in the circuit. First, analog to have all the apparatus to bring to the carrier frequency to access the spectrum. And second, the digital part to encode all that, to process all the 0 and 1s that comes from, for instance, the image you want to send, the video you want to see, or just your voice encoded. This is what we have here. We have some examples of circuits. We have designed that there at the lab, and you will see that with Magali and Marina in 1 hour. You will see it, you will touch it, see how we measure it. So that was my first part of the talk, and we always need something to break. So I put the picture of Monday night, where we were having the welcome dinner. So I don't know if you can see yourself there. We had a great time. It took me 1 day to recover. Drink too much. Was it nice? Yes? Yes? You like the food in Bordeaux? Yes? Yes? It's not the end. We still have other events. Okay. So now I go to the second part. See, now you are brainwashed. You remember Monday night, and then we can go to the second part. So the second part is how the evolution was carried out from the end of the 20th century to our expectation for the new communications, and we are talking about AI. So I've always had a question to the audience. Who knew that phone? Who used that? Oh, yes, few. Yes, I mean, yeah, I use it a lot. And this, I don't think you use that. Yes, no? Yes, I use it. You have to call, then to tell your message, and then it's sent. And this you don't know. It's pure in French. It's called a Minitel. In the 80s, everyone at home has this little computer, then, and it was quite the internet, our own internet. You can book some train tickets, flight tickets, whatever. Well, the screen, the resolution was not so good, but well, at least you were able to chat. We don't have Facebook on it, but kind of. Let's say we were very in advance for that. And then it passed away with the internet, of course. I'm talking about Martin Cooper, so same, what you have seen before. And this is the way we made the progress. So I would always like to know who is doing what in terms of technology. So I talked about Martin Cooper. There is a fun fact about him. He met Natalie Imbruglia. Remember Natalie yesterday afternoon for the training on cadence? The longer. So yes, they met together in 2016. That's the very important fact. And this is me. Oh yes, really important. Sorry, I forgot my slide. So this is me when I was young. 1983, I was 1 year old, and this is the first time I met my first silicon. And that's true. It's two pictures. And on the right, at the same time, I met my very first phone. This is my twin sister. I have a twin sister. And then, as you can see, yes, the phone is exactly the one you have seen in a few slides before. So just to tell you that it's a whole story from the 80s. When I say 40 years, that's my age, and that's why I was so tired yesterday, of how we went from all these features there. You can see the camera, whatever, compact disc. I don't know if some of you knew about the compact disc, VHS, and all that together. Well, we achieved that 10 years ago to have that on a single device, the smartphone you have today. That's so normal for you. For us, it was clearly a complete revolution in the world. We have seen it. And thanks to the miniaturization, this is what I was talking about before. Now in a chip, I said that we have tens of billions of transistors. The main invention of the 20th century is the transistor. And tens of billions is enough now to produce the signal processing to implement the artificial intelligence. When we say artificial intelligence, it's of course neural networks, all the signal processing, not to have dedicated algorithm, but to find with intuition, to solve with intuition some problems. So we can mix the two of them. The computing power that makes the artificial intelligence possible and the integrated circuits to communicate. And this is what I'm going to detail right now. That's why I call it, we connect the intelligences, the human intelligence and the artificial intelligence. So thanks to ST, represented by Didier, we go faster and higher in frequency. And that's the exponential data exchange we have since the beginning. So you have here, it's an exponential, it's per month, exabytes per month. More than 70% of the internet is video, is streaming. And half of the streaming is, let's say, non-informative at all. That means that we exchange a lot of data for nothing. But, well, how can we rule that? Can we reduce it? No. So we have to follow the trend and to propose always better circuits. This is the new 5G, the very first 5G circuits. We need to access multiple frequencies at the same time. That's why instead of proposing a new circuit, they said, okay, we're going to put together many circuits on a single die, we fabricate, we sell, that's it. All together. Several receivers, several transmitters. That's very complex. And that means that we don't care about the efficiency. The energy efficiency is really important. We go into a war. I mean, we don't make any progress. Didier was saying, okay, we need to improve by 14 the efficiency of our network. But if we continue to glue together some circuits, it's not efficient. And same here on the right, we can see the complexity of the transceiver. I was saying that in your smartphone. It's very complex circuit. It's exponential as well. And so I said that I was talking about Greta Thunberg. Greta Thunberg, she's not happy, like most of the time. She's not smiling there. She's not smiling. Why? Because the circuits are not efficient at all. 10 to 20% of the CO2 on Earth comes from electronics and from data that are exchanged for nothing. Can you imagine that? Some people complain because I take too much, I travel too much by airplane. Say, oh, François, you are responsible from all this climate change and so on. Say, no, you are responsible because your smartphone will consume more CO2 than my travels. Yes, now it's higher. So Greta, she's not happy. And we try to make Greta happy. How? So if you sum up your smartphone, it's always digital to analog conversion. And the limit there, this is what is power hungry. How to convert a complex information into an analog signal. This is what Didier showed. Also, with those limits, you have seen all the dots, and we approach to limits in terms of performances, in terms of power efficiency. The bottleneck is there, the data converter. We need to respect the resolution, the integration limited by the technology, the speed of signal processing, and on the top of it, we have the standard, because we need to respect those frequency standards to communicate in the world. And for instance, I like images. For 5G, we need to access to the spectrum from 600 megahertz to 5 gigahertz. That's for the very first phase. If you have 5G on your smartphone, this is what you have right now. But with a very high resolution. And the high resolution is 60 dB at least. 60 dB is as if your circuit is able to listen to a fly and at the same time to the rocket, Ariane 5, I don't know if you know Ariane 5, it's a European rocket, so it's quite loud, a rocket, and to understand both of them. I think when you are close to Ariane 5 taking off, you cannot listen to the fly next to it. Well, our hair is not good for that, but your circuit has to do it. And same, this is Jean-Claude Van Damme, so he's from Belgium. No, yes, Jean-Claude Van Damme, you have to deal with a very wide range of frequencies. So for us, it's two-dimension critical and to get circuits that is able to do that. High precision at the same time and multiple channel. Exactly the same picture Didier shown. It's from Boris Merman. This is very famous survey of performances of the conversion. There is a reality, all the circuits done before fabricated, and this is our dreams. See, we are quite far from the dreams. We push every year, but it's going to be more and more complicated to achieve that. And when I talk about 5G, and we will have to 6G after, it's not terabit per second, it's just 1 gigabit per second. Now we are able to achieve it, but we want it to be cheap because you buy your smartphone for a few $100s, not several thousands of dollars. Yes, except for the Apple addicted of iPhones. Yes, you are ready to pay for that. Yes, but you don't pay for the circuits. The circuits are the same price. You pay just for Apple. Huh? You send your money to Apple. Yeah, I send my money to Apple. And this is an iPhone. But with the increase of data rates, we need always more. And it's more frequencies, more features, more signal processing, and at the same time, we don't want to pay the price for it. Must consume anything. Didier has shown that the power consumption has to stay the same all the time. So you have more things, but same power consumption. It has to be cheap and access to the whole spectrum, of course, to prepare the next connectivity. So how do we make it? We have the radio frequency integrated circuit, as I said. I'm going to talk today about our project. So the one on the right about Hermes 6G. But before Hermes, we had another project, which is called Aggregate 5 for 5G. And we combine that here at IMS Lab to prepare the next generation of circuits of communication. And this is where we assemble several technologies. So as I said, we're going to target 6G, but the question is, why 4? After 5G, okay, it's easy to say that we're going to have 6 and then 7 and whatever. But why 4? It's to connect the unconnected things, people, whatever, intelligences. And this is there, what we see, what we can forecast for 2040, that we will connect together some robots. So maybe you have seen on the news the robots from Tesla. you know, the very smart one that will replace us for all the things we don't want to do. Yes, so they have to speak together. High data rates are required for that. They have to exchange many information. Same, we put chips in our brain, and I think you'll see that this afternoon or tomorrow morning. Yes, so we can discuss a lot about that. I don't want a chip in my brain, but well. That's why I've called cybers there. And well, at the end, we have a smartphone to communicate right now. But what can be better than the smartphone? It's telepathy. Telepathy. You have nothing, and we can just think together and share. Well, that's science fiction. So, what is the principle? And I have a question for you. It's an easy one. Which figure has the low number of dots? The lower number of dots? 1 or 2? Where there are fewer dots? Yes, it's 1. Yeah, sure, it's 1. Yes, I know that. But it's the same information. You have the same information on both pictures. It's because one has the time information and the other one has the frequency information. And each dot will represent a power consumption. Same cost, let's say. So if you want to design a circuit that consumes less, of course, you will opt for the most efficient one, so the frequency one. And what does it mean? That instead of using time information to convert signal for radio frequency, we will use frequency information. And this is what has not been done so far, and this is what we are doing at the IMS lab since several years. We convert information in the frequency domain. And when you think about frequency, you think about frequency Fourier transform. Do you know Fourier? Yes, it's very famous in France. He's French first. His name is Joseph, and he was a good friend of Napoleon. That's true. 1815. Yes. And they went to Egypt together, etc. Well, it's a whole story. But there's another guy, American, this one, named Joseph, exactly the same. It's completely by chance. And his name is Walsh. He invented like a Fourier transform, but digital. And this one combined two things, frequency and time. It's what we call sequential. And when it's digital, 0 and 1, it's easier to use in integrated circuits for electronics than analog. We know how to do digital. And plus, on the top of it, with a high density of integration, it goes better and better. So we will use those transforms to switch from time domain to frequency domain. And Walsh, so I said he's American. Well, he did his postdoc in Paris. So you can do like he did, come for your postdoc in France, and if you're looking for a place, you know that you are more than welcome in Bordeaux. This is advertisement time, okay, for your after PhD. And well, yes, he was a big boss. As you can see, he worked with John von Neumann, who invented the processor. So the question I started myself is how to switch from time to frequency. When you sum 3 harmonics, you can make a square wave. You've learned that at school. That's correct? 3 harmonics, so continuous wave, Maxwell, and you can have a square wave. And my question is, can I sum some square wave to have a sine wave, the reverse? And the answer is yes, this is exactly the Walsh transform. Walsh summed some square waves, so he has weighted every square wave, like the harmonics, and he produced a sinus. It's exactly what we're looking for if we want to communicate, like Maxwell did. We send the sinus over the hair. And this is what we are going to process into our circuits, those sequences. So it's a whole mathematics that was developed by Walsh, but the origin was from Jacques Hadamard. Jacques Hadamard is a French mathematician from the end of the 19th century. And the fact is, he was associate professor for his first position here in Bordeaux at the university just nearby, well, downtown, in fact, at that time it didn't exist there, but Jacques Hadamard, who created all that, was professor there. And what we have demonstrated at the lab is that using this algorithm of Walsh, we were able to generate some modulated signal. I mean that I can use 4G or 5G using this way of doing it. So how do we do it? We take the sequences of Walsh, you have there, the square signals, And we had some coefficients to weight them, and we sum them together. What I did? Addition. That's good. I can do it in the circuit. It's a plus. Okay. And weighting, it's like I amplify more or less. I can do that as well. It's quite easy. And you have your signal. You check that it's compliant with the standard. This is what we've done. We use MATLAB. Do you know MATLAB? Yes, we use MATLAB. We say, okay, that works. We evaluate the quality of the signal. It's using some metrics like EVM or SNR, signal noise to ratio, and we check that it fits with the mask of the standard. And what you obtain at the end is a circuit, which has been designed here by Pierre. Pierre is there. He works in 3 years to design the circuit. So designing a circuit takes hours, days, nights, whatever, 3 years at least, to do it. Yes, that's challenging. He puts all that in a chip, 1 millimeter square. And the efficiency is 0.34 picojoule per bit to convert exactly what I've seen before, 600 megahertz to 5 gigahertz with the resolution. This is so far the best-in-class converter in the world for 5G. Because we compare ourselves, as you can see here, well, we are still in the race. Yes, great. So yes, she smiles there. Yeah, it took me hours to find a picture with Greta Thunberg smiling. So she's really happy. Because if we have all that chip in our phone, we can divide the power consumption at least by 2 in the world. Okay. The other thing is, the higher you want to go in frequency, the worse will be your components, the technology, CMOS technology. I was talking about it yesterday at the end of the tutorial about cadence, where you have that capacitor. If you've seen that, the square wave is no more a square wave. It's like the shape like this, exponential shape. It's exactly the same for every component. At least where there is a transistor, there are non-linearities. Non-linearities, it's our daily lives with electronics. And we need to get rid of them. When you're low frequency, you can manage it. When you are high in frequency, it becomes difficult and difficult, more and more difficult. Especially with 5G FR2, second phase, which goes millimeter wave, around 40 gigahertz. And then higher in frequency with 6G. So all this is nonlinear because CMOS technology is dirty. It's cheap, but it's dirty. That's normal. There's always a price to pay. And all these nonlinearities will affect the spectrum. When you want to send what is here in blue, you will have some products, whatever pollution of the spectrum, what you have in red there, because it's nonlinear. There are many products that will leak in the spectrum. And you are not allowed to communicate in other bands because you have to respect the standards. So we need to linearize the spectrums. And how we linearize? Okay, we take the red, we subtract it to the signal we want to send, and then you have only the proper signal. This is the way we linearize circuits. And the higher it is in frequency, the more complex it is. It's always about trigonometry again, and there are millions, billions of parameters. When I say millions or billions, you understand where I'm coming to. Now, who can solve equations with millions or billions of parameters? Not a traditional algorithm. Of course. So linearization is the key. And we still have our watch. Remember watch. It was about coefficient. My information is encoded with coefficient. What we discovered is that basis is the best one to have the accuracy for the communication. When I say convergence, the power to linearize some circuits and the complexity, it's not complex at all because it's directly the number of dots, few dots, okay? It's frequency. And it goes from exponential to linear in terms of frequency. That's great. Instead of billions of parameters, I still have 1 million. It's better. Yeah, it will consume less power. And this is what you are going to measure by yourself Friday morning with Maxon. Maxon has developed the whole structure to linearize what we call the power amplifier. Power amplifier, you remember that circuit, common emitter, in bipolar or common source, you know, minus GM, RC, whatever, or RD. It's how we amplify a signal. The transistor is used to amplify, but it's non-linear. Here, what you have on the left, the power amplifier will bring more and more power, but at arriving at a given power level, it doesn't amplify anymore. This is what we call the compression point. It will make a saturation. What is saturation? It's when your sine wave will stop being amplified and it will be more and more like a square wave, kept at the top. When you cut a sine wave with just pure harmonics, you are more like a square wave, so other harmonics will come. And you are going to pollute your spectrum. We don't want that. We want to avoid it. And if your circuit is not properly designed, see, this is what you have on the right. The right is how your signal is modulated with the dots. It's 0 and 1. Then it's a cloud. You cannot recognize what is 0 and 1. And the spectrum you have there on the completely right, it's okay at the beginning, but then you have shoulders. The higher you go in frequency, and you're going to pollute the other channels. So you will measure that Friday morning, and you will see how we can compensate that. The answer is to linearize. A linearization is pretty easy to understand. Your PA, power amplifier, you can see here, it's like a logarithm in its characteristics. And if you want to compensate a logarithm, what do you put in it? An exponential. Logarithm of an exponential is just sorry, I don't know the word in English, but this is what we have here. We have compensated completely the behavior of the PA, which is not linear, by creating what we call a pre-distortion. You pre-compensate it. The fact is that the green curve is the one that have to integrate the millions or the billions of parameters, because you can get different frequencies, different phase, different amplitude, different temperature. The room, yes, is not always at 300 Kelvin, of course. It can be very cold, it can be very hot, and then the behavior of the electrons, same, it's always a story about electrons, will change, and then you have another characteristic. Also, not only about temperature, it's like myself for, again, Monday evening, aging. When your PA is new, it works perfectly. But with age, when it gets older and older, it's not the same. It needs time to recover. Insane. Like me, took one day. I'm like the PA. So my characteristic is changing over the time. And same for the battery of the pointer. No. That's okay so far? You understand? Yes? We have made a long journey from the whole story of communication to the circuits. And how you translate that? Those characteristics can be translated into equations. It's infinite equations. It's like, how do you call that? Taylor's formula. When you have local extremas, blah, 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 you can expand on some given points. And this is what you have here. On the left, with this curve. And then on the right, we will observe how the characteristic is going to be modified. That's why you have a cloud of dots there. It's because it's an in-between, like a Monte Carlo simulation you have for your PA. And what you want to do, you want just a line, a straight line. On the top of it, it's more and more complex. We have what we call memory effect. It's like the aging effect. Your PA can be stressed sometimes. And, well, what happened before can affect what's going to happen next. We've taken all this equation, and what we have discovered that when we put it in the Walsh domain, so the frequency, the dots, remember, it was coming from exponential complexity to linear complexity. It's purely mathematics. And it took us like 1 year to translate that. It's not that easy mathematics, but it worked perfectly. And we have designed that architecture. That architecture you will test. It's how we, instead of converting time, we convert frequency, and we apply it to radio frequency in its all as a whole transceiver. This is some figures when we have demonstrated that this algorithm, for instance, for the pre-distortion, I mean to linearize a component, it's 10 times faster, it's better, 10 times faster, and will consume 12% less for better performances. So that's great, that's a benchmark. Here you have the same view, saying that we take the shoulder and we put it down, so it works, MATLAB results. I don't want to go in details, it's quite a lot of information for you. What you have to remember that it's a new technique. And using that technique, we said, okay, it works for few gigahertz, traditional communication, 5G, let's say. Can we use it to linearize some components at higher frequency? I mean, the one for 6G. As Didier said, 150 gigahertz, very high in frequency. Can you imagine the characteristics of the transistor there? It's not so good. The power that is provided by the transistor is very hard to push. So you need linearization to be able to meet the 6G specification. What is 6G? I put the exact same slide I've had for the 5G, and I put 6G on it. It's more communication, more data rate. What we wanted, low power, as Didier said, same power consumption. Instead of 1 gigabit, I said 10 gigabits. Didier said 1 terabyte. Okay, why not? We need to use CMOS technology because we target a mass market. That's a break. Non, c'est bon, ça marche.
Ça marche.
Ah,
Pardon. Je te mets celui-là, il est là.
okay, that's a good break. There's no 6G in that. Just pure. That you can look at.
Ok.
Yes, so CMOS. CMOS is mass market because it's cheap. The cost of 1 millimeter square of CMOS type is 10,000 euros so far. It's 10 times to 100 times cheaper than the technology proposed by the GAN, IMP, whatever, ASCAP. So if you want to sell billions of circuits, that's quite mandatory to go through CMOS. And we know how to produce CMOS. I think that every day there is like millions of billions times more than ants on Earth of transistors that are produced. Can you imagine? It's 10 power 20, 30 number of transistors per day because it's CMOS. So we want to target that part of the spectrum at 150. And this is the famous attenuation I was talking about. See, it's not linear. You can find at 60 gigahertz that rate of absorption of the oxygen. Then we have the water somewhere. I think it's the one at 200 gigahertz. It's the water absorption. So that means if it rains, you're not going to communicate so far. And when it's humid, same. So we need to find some room to pass those 10 gigabit per second band in the spectrum. And the new millimeter wave is the sub-terahertz. It's around 150 gigahertz there that is not exploited for a range of only 100 meters, but that's quite okay. When you have two robots working together who are talking together, that's enough. Normally they are nearby. Or like the DSL, like Didier said, we have mini cell, for instance, the Wi-Fi in the room. So we mixed the two of them, artificial intelligence and Walsh theory. So Walsh are the core of the conversion of the radio transceiver, those mathematics to perform the conversion of information, and CMOS technology to be cheap. So what is the role of AI here? You have understood? It's to perform the linearization of the components, to make that mix of log, exponential equal straight line. So many parameters that only AI can solve it. So this is what we said, only the artificial intelligence can solve that. But we can go beyond that. This is the project which is summed up in one figure there. There is also another option we want to take to the AI. The AI is able to decide what band of the spectrum is available. We forget the standard now. There's no more standard. And the AI will say, okay, oh, there's no one communicating at that frequency. I'm sure I will use it right now. I'm alone because no one is using it. So it's purely opportunistic. We don't need a rule, we don't need a policeman because AI is able to speak by itself. I'm speaking right now, you are listening. See, it's a common thing we have together. We are smart, we are intelligent. Yes, someone can interrupt me. Yes. And I will stop speaking and you will speak. So I use now ChatGPT logo because everyone can understand that. Another point, I go higher in mathematics. Don't be afraid, we have only 10 more minutes. The thing is, if you go high in frequency, 150 gigahertz, there is something very hard to do, is to filter. If you want to filter a signal, you need to pay a very large price for it. This is what you have here. When you are in baseband and you have 10 gigahertz of band, you have what I call the devil twin. There, devil. It's the image, frequency image. It exists below 0 hertz. But when you make that multiplication of cosinus by cosinus to up convert or down convert, the devil twin, the devil, will appear in the frequency. This is what we call the image, this image frequency. It will appear, and we don't want it because we are going to use twice the spectrum instead of only once for the same information. So what we do traditionally, we filter it. We add a filter. The filter at 150 gigahertz, as I said, they cost a lot. So I said to my colleague, if we don't want that frequency, that image frequency, we need to reject that high frequency. Why don't we kill it when it's born there in the negative frequency? My colleague works on mathematics and said, no, that's not possible. It's not feasible. It's non-causal. Yes?
I'm just wondering, the image frequency you're talking about, is that the same thing as aliasing?
Same thing as?
Aliasing.
Exactly. Same thing as aliasing, yes. Aliasing, by something, you will, another word in French, but make some replica in the spectrum. It's exactly the same. It comes from the negative frequency, and we don't know. Yes, you can't see it. We can't see negative frequency. So why not we kill it when it's born? If we do that, boom, it will disappear, of course, and that's it. Well, there is a mathematical tool for that. It's called the Hilbert transform. Do you know Hilbert? Yes, he was a crazy mathematician. Yes, he was able to envision many things. But let's take an example. When you have a cosinus, this is the cosinus, remember, that carries your information. This one. So I call it the rabbit. This is what we have the rabbit, because the Fourier transform of cosinus is a rabbit with the two hairs like that. One negative, one positive. And you make the Hilbert transform of the rabbit. The Hilbert transform of cosinus is a sinus. Okay? So I call it a pharaoh, because the pharaoh is like that, okay, with the hands, but in the imaginary part, like that. And if you combine a rabbit with a pharaoh, well, you will kill one of the harmonics there and the negative one. Okay? This is Hilbert transform. So then you cut a hair to the rabbit. Well, this is a French joke, but I don't think you can understand it. The Hilbert transform will generate a signal which has only some positive frequency. That's great, because when you are going to mix it, boom, you don't need to reject this. The fact is, it's non-causal. I mean that you need to know, since the beginning of the universe, Big Bang to the end, what happened to reject perfectly the frequency. Do we need that? No, of course. We are engineers. We do like Earth. We connect wires, and if it works, we don't touch. Yes, we try to understand. And this is what we have done. We have translated the Hilbert transform into an algorithm with those boxes there, and we made like the convolution of a given window. I mean, in time, we store in a small memory some information, which is like it was coming from the Big Bang to the end of the universe, but it's limited in time, and we make some signal processing. Quite complex because, well, Hilbert, he was a crazy guy, but not so funny. He said that physics is too difficult for physicists. See how he was quite arrogant. He could have been French. It's okay, you're still with me? Yes, we're close to the end. And he proposed all that theory. We applied it to MATLAB for 5G. And what we have observed, that we were able to reject a signal just by signal processing before the up or the down conversion. And we tried to see if it was compliant with 6G in terms of reactivity, the time we need to store the information to process it. The order of scale was nanosecond. Nanosecond, in terms of signal processing, that's quite okay. We're engineers, we're here to make some trade-off, and I think nanosecond to reject 80 dB is good. Remember, we need to respect the standard, at least 60 dB. We are in that window. Tens of nanoseconds, that's acceptable. So we made it, but we said, okay, why not doing this signal processing using the Walsh mathematics? So we tried to mix Hilbert and Walsh. That's insane. I found only one paper about that. It was from Terence Tao. I don't know if you know Terence Tao. He's professor at University of California. He get professor at 21. I mean, he get his doctorate, his PhD at 15. This man has an IQ of 200 something. I was just able to read the title and the first line of the paper. I didn't understand not even a word of the paper. It was too complex for me. So I did like I'm used to do when I don't understand. I tried to same not to go for equation, but to do it by myself. And we have demonstrated that we can apply the Hilbert transform into Walsh and apply it to radio communication. This is what you have here in red, the same but cheaper. Why? Because you have the matrix here, which is those matrix, magic matrix to perform the Hilbert transform into Walsh, and there are many zeros. When there are zeros, a lot of zeros, that means that there is no signal processing at that time, no multiplication, no addition, nothing. So the complexity of the signal processing is low. This is what we have here, doing that. And we've applied it to our system with the Hilbert transform. So you have the baseband signal there. It goes through all the transform we've seen before to communicate in 5G, and then the devil you have there is rejected at the end. So we have two mathematics at the same time for our communication. So what I've done here, I've used Walsh and Hilbert. And how I'm going to use it with AI. I've seen that the mathematics are compatible. And that was a perfect language for AI. This is what I've discovered. Using the coefficient of Walsh, the mathematics of Hilbert, AI, the ChatGPT AI, has a perfect match optimization to communicate. And this is what we have done. The AI will speak directly into Walsh with Hilbert to communicate. So that was almost the end of this work. But you've seen 7G. We said, is it power efficient? The answer is yes, because AI will solve equations very complex rapidly. Instead of billions, it's millions. The complexity of my signal processing is not exponential, it's just linear. I will linearize, I will reduce the power consumption and increase the efficiency. But if I go on this way, same Greta Thunberg, for 7G, let's say to push a little bit more the specification, we need to cover twice the image length of solar panels to supply our future network in 2040. We cannot do that. Where are we going to live if we have solar panels everywhere? No. So we need to improve again the efficiency. And now I will close the loop with the first keynote speech about semantic. As I said, 50% of the information we send are useless. No interest. Yes, what is the temperature in the room? We need to monitor it all the time. Nonsense. And it's everywhere. It's trillions of circuits communicating. So what we propose is to do, well, signal processing at the edge. You always hear about that, edge computing, not the cloud, because then you are going to process your data somewhere in Sweden because it's colder for the data center, blah, 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 blah. It costs so much. It has to be at the edge with AI. And we're still looking for an intelligent and autonomous radio. And this one, the target is to divide by 1,000, 10,000 the power consumption. That means that we will prevent from communicating when there's no need of it. And I said, it's your responsibility not to go on the internet, and you will go wherever. So it will be the radio responsibility to communicate or not for it. And there is a mix of everything there, with especially the meaning. There's a breakthrough to come. So this is my last reflection about AI in the wireless communication. Effectively, we create and infer meaning of what is communicated, not 0 and 1. 0 and 1 is just pure data. We are looking for the information we're communicating, and this is exactly the same slide that was proposed by Emilio for the first keynote. John Bonneman, so the friend of Walsh, remember? Yes, everything is connected, as I told you. It's a whole story. There is no sense in being precise when you don't even know what are you talking about. So we just want to send some sense. And this is Warren Weaver. So you know Claude Shannon, but Weaver was a good friend. And Warren Weaver envisioned in the 50s that semantic communication will be more efficient in terms of power. It will save bandwidth. It will be more robust to noise. That means that your circuit doesn't have to be so linear perfectly. It can be robustness. Remember, Monday night when we had that dinner, there was so much noise, but we were able to understand each other because what you are saying has some sense, some meaning for the one listening. So this is exactly what Weaver said. The only thing he didn't have is the technology at that time. Fun fact about Warren Weaver: he did not meet Natalie Delta. This is very important to say. Yes, that's a joke. Okay, you're tired. And he was a collector. He was really interested about translation, automatic translation. That's why he collected many books about Alice in Wonderland in 42 languages. So yeah, his hobby was also to collect translated books. So we use the circuit I've shown before. But this time, instead of respecting exactly the standard, I just will use the coefficients of Walsh as a carrier of the information, and I will associate them. So I don't want you to understand the mathematics behind that. We are still researching on it. But we will take a risk and innovate on this. So coefficients are no more calculated for a given RF signal, but are used to carry the information, the semantic information. And we make that product and that sum, as you've seen before, except that we do it with the coefficient directly. And what we have is a pure spectrum, which is terrible. We don't respect everything. We violate completely the spectrum. But the information which is carried use the Walsh transform. This is what we call the OSDM modulation. We just invented it 6 months ago. Like OFDM, we have the OSDM. And why for? It's exactly what you know, Shannon. Shannon said, okay, let's put the whole pressure on the transmitter to get the 0 and the 1 perfectly. So the receiver has no effort to collect the 0 and the 1, except few errors there that are compensated, let's say no price or almost, by the, error correction codes and all these, but more and more mathematics. It's only based on that the fact the transceiver has to be clear, perfect. So he said always, who is speaking? This is who I am. This is what I'm going to do. This is a frequency. This is my data, a small packet of data in the middle of everything. And okay, have you well received? Yes, no, blah, blah, blah. Well, what we think about semantic, Weaver said there is no sense to be precise. For instance, we are in a job interview. I'm saying to you, you are hired, but I don't make so much effort. There is a lot of noise, and you listen, you are fired. So like, what is he saying? I'm fired, but that's a job interview. Automatically, your brain will correct it to fired, to hired. Of course, there's a meaning of it because we share the context. And it's exactly what Weaver wanted to do. No pressure on the transmitter, speaks like he wants, but the receiver will understand because there is a context. And you didn't see it on that side, there were 2 high missing because your brain automatically corrects what you read. Yes, see, you are the receiver and you have automatically corrected. So it's how we are going to implement that using our radio circuits, the one I've presented for 5G and 6G. I'll go quickly over it, but for instance, a language can be decomposed into symbols. This is what Emilio was saying. For instance, you are hired, it's you, are, I, hired. We have some syllabs. This is our language, human language. We can spread it like that. And see, it's a constellation. It's exactly the dots you have seen before for the digital communication. And we make an association with the coefficients. And it travels through the spectrum, physical layer, and then you collect it. But there's an error when you receive it. You are fired. But thanks to semantic and semantic mapping and extraction, you automatically correct it. This is what we call the level B of communication. Level A is physical, traditional. Level B is with meaning semantic, and this is where the intelligence appears for communication. I'll go rapidly through that. It's pure theory. We still have the level B and level A, exactly the first slide you have seen before with the digital to analog division there. And we have another way to see it. And same here, it's how we perform that conversion with the Walsh coefficient directly into the physical layer. So I propose to pollute the spectrum, but to communicate of sense. This is a movie in 1977. Have you seen it? It's about, so I don't know if we have the sound. Without the sound, it's going to be complicated, but as you can see the lights there, it's so it's third kind, close encounters of the third kind. It's aliens meeting humans, and they don't know how to communicate. They use some lights and sound, and at the beginning, okay, it's few lights, few notes of music, and then it becomes more and more complex. This is exactly the coefficient association I want to make between the meaning of the message and how to communicate here optically and with the sound, exactly what I was saying at the beginning with the beats, the valves, and whatever, but with our circuit. So sorry, there is no sound, but you can go on YouTube and you will find it. And yes, it's exactly what I'm saying, that it's Walsh, and you can see here the different colors. So I'm very close to the end. What time is it? Oh, almost time. I know it's a lot of information. But think what is semantic, from Shannon to Weaver. I'm using that coefficient and my circuit to convert information, blah, blah, blah. It's like when you meet someone. The first meeting, you don't know each other. You are purely in Shannon style. You introduce yourself. Who am I? Yes. Okay. Who are you? Okay. This is the message I want to give it to you, and I'm very polite. Of course, when you meet your partner for the first time, you are very polite. You are not rude. And for instance, you ask for the bread. Can I have the bread, please? And when you receive the bread, you say, thank you very much. Plus the first date. If it goes well, you have a second date, third date, fourth date. And then you start to live together. After several months, you know each other. No need to introduce yourself, who you are. Yes. You just ask, can I have the bread, please? You are still polite after several months. Yes. And when you get it, you just say thank you. No need to add more. If it goes well, after maybe waiting or whatever, several years, you don't introduce yourself. You live together. It's like the transmitter and the receiver, they are used to communicate. Do they need to introduce each other? No. They are serving every day each other, so that's fine. Are you going to ask for the bread? Yes, of course. Say, can you give me the bread? Or just the bread, please? Maybe no more please after several years. And that's it. And when you receive it, you're not going to say thank you. No need to say thank you after several years. You are shifting more and more on the Weaver side. What I mean that on the left, you have a lot of precise data, and I'm shifting to information. And at the end of the year, the whole life together, yes, you know so well each other that just we see hi. Yes, you can ask for the bread. Boom, no need to speak. And you get the bread. Yes. This is how it works. So this is semantic. I mean that the transceiver itself will completely adapt. And how are we going to do that? To use the coefficient, the modulation, the spectrum to linearize with Walsh, Hilbert, and all that together. What can generate all that? Artificial intelligence. So many information. And I'm not talking only about the common language. Language is many things. If you have seen that movie, Arrival, it's when the heptapods are coming on Earth to learn, to train ourselves to their language. Have you seen that movie? Come on, you go to the cinema. Come on, see Jordi. I keep asking him, have you seen that? No. Maybe you don't have Netflix in the Netherlands, I don't know. See how they translate their language, it's another way. We can imagine that two machines will create their own language to communicate the most efficiently as possible. And if they know better and better along the life, they will be more and more efficient in their transmission. So this is my last slide. And there was a gallery of characters I've introduced to you. There are a few there, just to show you that the trends and how AI will assist us for communications is to provide also always low-cost solutions with low consumption, low power consumption, high energy efficiency, and high spectral efficiency. And thank you so much. If you have any questions, you have seen many things. I'm sorry, I've covered large range, mathematics, and philosophy as well, history. Any question? Yes.
About the Walsh transform, so it's a directly discrete transform.
Yes.
So it's like a Z transform or DFT.
Yeah, kind of.
Is there like a continuous equivalent or?
No.
Okay.
No.
And if I understood correctly, so you use the Walsh basis because it makes complexity
Yes.
lower,
Yes.
and you need that from Volterra series.
The Voltaire series will describe the nonlinearities of the PA. Yes, and we have translated those series into the Walsh basis.
Okay, so good.
And it is more efficient, as you have seen. It's same again a matrix with a lot of zeros. It's sparsity, in fact. You use the Voltaire series are more sparse in the Walsh basis. That's why we still need some humans to imagine that, because it's not artificial intelligence who will take care of that. Any other question? What was a hard question you asked? You have understood everything.
I just didn't process it.
Yeah, that's great. Maybe online? I don't see any question online. Yes.
Not directly related to this, but you're using optics visually for communication.
Sorry, I don't
So
see.
you're using the optics visually for communication.
Yes.
So any thoughts on the roads that are using optical processing, that they're using it with, I don't know, PCM or linear computing, like the topics of this?
Yes, so I'm not taking care of that. I see it like a black box for me. Yes, I'm just taking care of the radio frequency content. So I don't have the answer for it. But your question is how to have the AI or the wiring communication for all that, for the whole network. There is diversity in like every network. This is just a part of the solution I've proposed today. The other part, it will be an assembling of several technologies like you have in that summer school. And I don't have the answer. Are we done? Yes?
So from my understanding, the AI called PA, we try to fit the curve of the PA and make extend the working region. So in somehow from hardware people, you can build it more into the design. And also for the PAs, for the precise for the design, the structure, we need to develop different models for memory. Is it general thing?
Yes. I think I've understood what you mean. That here you have a digital pre-distortion technique. Can I apply it to any PA? The answer is yes. What you will do, you will apply to different PA finally. Also, the designer tries to do always his best to get the perfect S parameters, etc. Can I do like a dirty design, and then the prioritization will do the rest of it? The answer is no. We still need some good designers to make the first step to have a good design. I'm thinking about output matching network or input matching network, etc. It has to be matched. And to answer a question that was written in the chat, same with the S parameters, we feed the AI so it can do its best, but not absolute compensation. This is what we give to the AI, the S parameters, and it's amazing. I mean, that's what the first results with the autoencoder and so on and so on. I'm not familiar with the exact language of that, but it provides some in simulations very, very good results. But at the beginning, you need a good design. Yes, or at least with some buttons you can play on it to adapt, compensate. Same with capacitors, for instance, variable capacitors at the output to play on the harmonics or whatever. Yes, that was your question. Yeah. Okay. So if you're looking for a job of power amplifier designer, you will have a job for the technology. Yes. Yes. Don't worry about that. Yes.
On the PA, we need to have a pre-distortion block. But how you mention this pre-distortion block?
Yes, it was in the schematic. The pre-distortion is when you close the loop. So I didn't detail what you mean is that I didn't detail how the pre-distortion was carried out. Yes. Went quickly over it. You have more details with Maxandre. It's there. You have more details with Maxime Friday morning. He will give you an introduction, a 30-minute introduction, exactly describing that, how it works. A lot of the questions, same again. But what you have there, we convert to Walsh on the left, we convert to Walsh on the right, and this is what you have here in the Walsh domain. So here you have X, Z, Y. This is the compensation. Yeah, with the update of coefficients. This is the correction. The DPD is exactly there.
So you do the update of parameter based on neural network, or
Yes, the idea would be that fully agnostic of the component itself. I mean, the AI can at the beginning, very first time, sweep the characteristics and make like get some coefficients to get some vectors of corrections, and rapidly that's the convergence approaching to get a whole library of corrections, large number of frequencies, combination of amplitudes, phase, whatever. And that's why I was talking about billions of inputs. But normally the convergence is 10 times faster, so you can sweep and learn a lot. Most of the time now, your PA is just trained for a very narrow band and few combinations. The idea is to have 20 giga wide band compensated with all the possibilities, any kind of modulation. As I said, also you have time into account. What happened before can affect what will happen after. Much more complexity. There's other question. Okay. Why not you are focusing on analog predistortion instead of DPD? Because we want to connect it to AI to make it flexible. Recently, in some Wi-Fi module, analog predistortion circuits are utilized. Okay, thank you very much. AI model is used in both transmitter and receiver section to optimize the performance. That's true. That's correct. Yes. And at 6G communication due to high frequency load modulation will be there. Sorry, I don't understand your question. Scott, any other question? Yes?
I may need some clarification on how you apply the semantic AI. So take this example. For example, you want to transmit an image, and you encode it to some digital signal, and give it to a transmitter, and then receiver, and then decoder.
Exactly.
And how you apply the semantic images?
Yes. Okay. So I'm not the expert. I work with CA for that in France, and they have developed a model of semantic extraction. So the semantic extraction are all the rules to start from a given set of concepts. Okay. Concept is what are the situations you are facing for, and the concepts are translated into semantic symbols. For instance, our language is a concept. And when I speak, through the language, there is a whole history, many things that comes with the language. But the symbols are my voice and the syllabs. So same, you can imagine that for the rest. So I'm not taking care of that. I rely on the colleagues working on it. And what they give to me is the symbols and associate it to transport it through the physical layer. Yes. So I'm sorry about that, but you can look what Emilio Calvanese, the first speaker on Monday, who has written on it. He's written many things in 2 years. So you have all the information online. Yes, PA, how you, if the PA impedance changes, the PA can be abnormal in a high variation load. That's true. So the load modulation is required. That's true. So for the load modification, it's what I've called the output matching network. That's why we still need some physical implementation of some variation, for instance, one capacitor here and there to modify the impedance. And then it can be controlled by digital words, by the circuit itself, same to dynamically adapt and find the best trade-off for the energy efficiency or the spectrum access. Okay, we're close to eventually. I think you need a break. Yes, 10-minute break. I'm so sorry for all the density of information. And thank you again, and have a good day. Thank you.